Only after that you can do the evaluation. Is that right?
So I'm here to give you the answers. At least some answers, because we haven't covered something that's in the question paper, as you probably see. Yeah? Okay. So we have half an hour, and then I have to go somewhere else, apparently. So where is that place? Very good. 100 points. Who said that? Are you from there? Priya? Slides not showing up. HTML. HTML? Huh? Remove it. Re-enter it. Ah, okay. Let's. Huh? Wait. Yeah, we got it. Yep. Okay. We got it. Thank you. Okay. Half an hour. So in half an hour, I have to give you all the answers. Okay. So the motivation to do this study, right? So if you see causes of paralysis, right? And as you can see at the bottom, what is the winner there? What has the most number of cases? Stroke, right? Stroke, multiple sclerosis, MS, right? And then is spinal cord injury, right? Cerebral palsy and other causes, okay? And these plots, this data are from this website, ChristopherReeves.org, okay? And they have a foundation. Who is Christopher Reeves? Does anybody know? Christopher Reeves, has anybody heard his name? Sir? Christopher Reeves, our generation actor. So he was the first Superman. Okay. So this actor, he was the first Superman. Okay. And he was one fine day, he was riding a horse, and the horse was unruly, and he fell with head down and neck, spinal cord injury. And since then, he was paralyzed. Overnight, he immediately, from superhuman to individual with disabilities. Okay, that's why he has this foundation, and his wife Donna also has this foundation, Christopher and Donna Reeves Foundation. Okay, so and there are also other causes of paralysis, motor vehicle accidents, sports, yeah, but again, not to the scale of stroke or spinal cord injury or multiple sclerosis. Okay. These are data from the US, but it'll also give you an idea. Okay, you see the dark spots. That's where the incidence of stroke is larger. Okay, those dark spots. Okay, and in the US, there is a culture of drinking tea, and particularly in those dark spots, you see that? Particularly in those places, they have tea with sugar. So they are called sweet tea states. You know, there are some who have tea, but they don't take sugar, right? Right? In those states, they have tea, they take tea with sugar. That's why they are called sweet tea states. If you Google sweet tea states, you go to images, it will show up. That part of the US has those states, and you see why it is coinciding, right? Because diabetes, yeah? You see the first opening remarks, the whites, yeah? Remember? Sugars, salts, remember? Yeah? All right. So that's the motivation. So the motivation here is to rebuild instead of repair, right? Repair is stem cells. I don't do that research, right? So so we are building neuro-controlled prosthetic devices. So that's why we're calling them neuroprosthetics, neuro-controlled prosthetic devices. So how can we record brain waves? How can we record brain waves? Huh? EEG. EEG. EEG is one of the ways of recording brain waves. What else can be used to record brain waves? Huh? You can just read my mind. Just by looking at me, you can read my mind. How can you record brain waves? Huh? MEG. What does that stand for? MEG. Magnetoencephalography. Yeah. Okay. That is one way to read. Yeah. What else? How else can you read? MEG, EEG. The magnets, remember? fMRI, MRI, CT. Those scanners are also reading your brain, right? Yeah. Okay. So brain recording modalities, there are two of them. If you want to majorly classify, there are two brain recording modalities. One is invasive. What is invasive? Huh? Surgery, it needs a surgery, right? You need to invade. Yeah. So that is invasive. And then is non-invasive, right? What is an example for non-invasive brain-machine interface? What does it use? Non-invasive, huh? EEG, yeah? So electroencephalography is a type of non-invasive, yeah? Okay, so this is a good picture that tells you where is what, okay? So I'm going to use this pointer. This is actually larger, so let's do this, okay? So before even we get to modalities, so this is the brain, yeah? This is the cortex, yeah? So we saw the videos, right? So this is the cortex, yeah? And on cortex, there's a fine layer, okay? There's that fine layer, right? And that's called dura, okay? And after the dura is the skull, and on the skull, what is on the skull? Is the skin, right? That is called scalp, okay? Scalp, skull, dura, cortex, okay? All right. So the most non-invasive, right? The most non-invasive is how far you're from the head, right? How far you're outside the auditorium, remember? Yeah. Yeah. So if from Mahindra, right? Yeah, from Mahindra University, yeah. MEG is like these magnets that are sitting outside the brain and they're recording your activity inside the brain. Okay. They are physically, honestly, not touching the brain, not touching the surface of the brain. Okay. So that is MEG, magnetoencephalography, and other magnets are like that, MRI, etc. Okay. And then is electroencephalography that sits on your scalp, right? That's why when you put those electrodes, EEG electrodes, you have to separate the hair, right? You have to separate the hair and make the contact with the skin. That's scalp, okay? All right? And then you go inside. Now this is all invasive. Once you crack open the skull, it is invasive, right? Invasive, you can put electrodes on top of the dura, right? So these are called epidural because they are on top of the dura. These are called epidural. And you can go under the dura, and this is called subdural. Epidural and subdural. Okay, so you can put those electrodes. So that's like what they do for epilepsy. You put the sheet of electrodes on the surface of the cortex, whether under the dura or above the dura. What do you think is better, under the dura or above the dura? Huh? So what do you think is closer to the cortex? Under the dura, right? Under the dura is closer to the cortex. Okay, above the dura is away from the cortex. Okay, but above the dura is better because it is safer. Yeah. Okay, but usually ECOG electrodes, they're all below the dura, subdural electrodes. Okay, um, so you can start recording um, not from single neuron, right? Right? You're recording from about 1,000 neurons with ECOG electrodes, electrocorticography. So you can write this down. ECOG, ECOG. What is ECOG? Yeah. So don't confuse this with EKG or ECG. What is ECG? Electrocardiogram or electrocardiography. What does that measure? Heart, right? It's not brain. Yeah. Dil dimag, dono alag alag. Yeah. Yes. Okay. All right. So ECOG is electrocorticography, right? Sheet of electrodes on the cortex. Okay. All right. And then that is two types: subdural, epidural, right? Subdural under the dura, epidural above the dura. Okay. And then using these electrodes, okay, using these electrodes, you can actually monitor epilepsy, find what is the part of the brain that is misfiring, and it helps clinicians in finding that part of the brain that is misfiring and take it out. Okay, you can help the surgeons find that place. Okay, and then is single units. Okay, so this is the most invasive type of brain recording, and also the most closer to the ground truth. Okay, using these electrodes, you can record from single neurons. Single neurons. You can record from single neurons. That is single unit recording. This is the most invasive type of technology. Okay, the sleeping batch is already answering the questions because I'm giving them the answers. Huh? So they are already looking at the question paper and like, acha, ye iska answer. Okay. We should not name you sleeping batch. You're the most active batch, right? So you guys are actively working. Huh? Before even I complete the question, they will answer. Huh? Okay, so these are single unit recordings. Okay, using those same single unit electrodes, you can also pick up what are called local field potentials. Okay, these are called LFPs. Okay, these are not activities of single neurons, but these are activities of collective neurons, like populations of neurons or networks of neurons. Those are LFPs. Okay, so what is the most safest among these? Safest is EEG, right? So we'll start with that. So EEG can be used for brain control, right? This is non-invasive. This is promising for therapies, okay? It is used actively in ADHD, right? And it's been used for now 30, 40 years, okay? All right. It was not suitable for precise control because they thought that the signals are very, very noisy. But recent developments are showing a lot of promises that actually using EEG signals, you can do a lot, okay? Here's a quick example. Not from our lab, but here's a quick example that you could use EEG signals. You could train yourself. So how many dimensional control is this? Is it two-dimensional or is it three-dimensional? What do you think? Three-dimensional, okay? But you see what you're seeing in the matrix, in the picture down there, is only two-dimensional, okay? So this is actually only two-dimensional control, okay? the third dimension is automatically being taken care of. Once you reach the position, the arm will go and put an object, okay? But that's not brain control, okay? So this is a two-dimensional control. That two-dimensional control you're able to accomplish using EEG, okay? All right. So the other extreme is single unit based recording, and that's the most invasive, right? Like I said, this is very invasive. This is very, very accurate in real-time control. Okay. And it is also good for high speed, precise control. If you want to control a robotic arm in real time, right? Almost moving at the speed of human hand, for example. For such recordings, this is the best. Single unit recordings. You're actually recording from single neurons, but this comes with very, very high risk. Yeah, because this is single neuron recording. So there's a lot of animal studies that were done, and there are some human studies that were done as well. But again, this comes with the risk. Okay. So now we're going to see some trends in biomedical, I'm sorry, brain machine interfaces research. And we're going to see some trends. Okay. So the first one we're going to see is from binary decision to four-dimensional control. This was the first leap. Okay. From binary decision to four-dimensional control. Okay. So, okay, very similar to the previous one. We're going to see some videos. Yeah. And I'm going to ask you guys some questions. Okay. Yes. Ready? Yeah. Okay. So here's the first one. Priya, can we increase the volume?
Scott Mackler was a husband, father, and successful neuroscientist when he received perhaps the worst news imagined. At the age of 40, he could run a marathon in 3.5 hours, but it was about that time that he discovered he had ALS, Lou Gehrig's disease. His brain was losing its connection to virtually every muscle in his body. Near total paralysis would also stop his lungs. He didn't want to live on a ventilator, so 9 years ago, recorded this message for his new sons. I know the kids are always months of blood, trying, and life goes on, and only one thing will along the way. And I love you very much and help you. This is Scott Mackler today. His mind is sharp as ever, but his body has failed. Doctors call it Locked-in syndrome. Scott and his wife Lynn work to communicate with about the only thing he has left. That's right. And for ill close away to discover some. It is. But recently, Scott found a new voice. I apologize for the quality of the voice. Scott wrote these words one letter at a time, with nothing but his thoughts, and the help of what's called a brain computer interface, or BCI. He wears a cap that picks up the electrical activity of his brain and allows him to select letters simply by thinking of them. Then the computer turns his sentences into speech. Finding will help us and what other people put words in my mouth. Well, this is a very unusual order. 60 minutes, we've done something that we never do, and that is we submit the questions in advance because it takes some time, a little while to put the answers together. So we need some time. So I understand that earlier question of this disease. You said that at the point you had to go on a ventilator, you didn't go on. But today you are on the ventilator. Curious about what changed your mind. It does not still communicate. It isn't fast. It takes 20 seconds or so to select each letter. Scott told us it took him about an hour to write the answers to our 16 questions, but he writes well enough to continue his research and manage his lab at the University of Pennsylvania, where he still goes to work every day. Is the system even test the size, for example? They, if the system somehow stay away from it. I could work it on this model. Good work on this model.
Okay. So when is this video from? Already 25 years old. Yeah. So at the age of 40, he got a disease. Does anybody remember the name of the disease? ALS, right? Look that up. What is it? ALS, amyotrophic lateral sclerosis. Okay, ALS. Okay. So what that means is that neurons in the brain are dying. Okay. So he's losing parts of the brain. Okay. So and so that's how he has become, right? And that's called locked in syndrome. Okay. Locked in syndrome. Okay. Please write that down as well. ALS, locked in syndrome. Okay. And what is left? What can he do? Eye movements. Yes. Very good. Okay. So he only has eye movements. And he passed away. He worked somewhere, right? As a professor. Where did he work? That was in the video, right? Did you notice? UPenn, yeah? He passed away in 2013, okay? So, but in the video, they said, what is the speed of typing with brain in this video? Yeah? 20 seconds per letter, right? So now you are going to write the exam, right? In a little bit. Can you write at that pace? 20 seconds per letter? Huh? You will need 1 week, right? First, you have to think. You don't even know the answers. Huh? And on top of that, now you can only write one letter in 20 seconds, right? Now you will choose 4 letters. EXIT. QUIT. Isn't it? Yeah. So it is very cumbersome for us to type one letter in 20 seconds, right? It's just, yeah. So for answering 16 questions, it took 1 hour for him. Yeah. So this is one-dimensional control. So how is he controlling? Yeah. Yeah. Huh? He's thinking the letter and the letter is coming. Huh? How? How did that happen? So there you saw that matrix, right? Matrix of letters. Yeah. That matrix of letters are shining different letters at different times. But when I want a letter that I'm thinking, right? When that shines on the screen, that immediately elicits a potential in my brain. And that is called P300. Okay, there's a peak in my brain signal that happens after 300 milliseconds after there's a shine in that letter that I'm looking for. Okay, and that is called P300 wave. And like P300, there's also N100, N300, and there's different kinds of Ps and different types of signals are there. Okay, but with this P300, yeah. What potential? That right. So these are event-related potentials. Okay, so there must be an event. There must be a surprise. There should be a stimulus. There should be a response, and that evokes a potential. Right. So that's why these are called ERPs or event-related potentials. Okay. All right. And so this is one-dimensional because at a time you're choosing either yes or no to that letter. Okay, and you're doing it several times. That's why it is taken that long. Make sense? Yes. We use this type of a control in the arm control that I showed in part 1. Remember, we use brain controls to move the arm up, down, left, right. We were doing exactly this. Okay. All right. So now, so this is one-dimensional control, right? Yes or no, 1D. Okay. From there, we move to 4D. So this was a big leap. Okay. And let's watch that video. Pay attention, and I'm going to ask some questions again. Okay. All right.
watching the monkeys move and record corresponding signals is. So what is that? Schwartz started to figure out that relationship. Able to connect the monkeys were within days, the monkey operated the car to it was its own. Operated. Up down the Japanese, the monkeys operate the song. I think the phones, absolutely. The government right there.
So I got edited in a bad time. He says, we think the human can do much better. Okay. And then we did the studies and human did much better, right? So in the video, what are the 4 dimensions? Well, it's 4D control, right? How is that 4D? Huh? Yes, that's right. That is the 4th dimension. So, right? 3D, right? Arm moving in 3D space, X, Y, and Z dimension. And then the gripper. That was the 4th dimension. Okay. So that monkey, he had electrodes implanted in M1. What is M1? Primary motor cortex, PMC, M1. And we were using those invasive brain signals to control that robotic limb to move. But how did they get that? How did they get that robot to understand the brain signals? How did they do that? First, they recorded monkeys' movements, and then they recorded brain patterns. Then they did pattern recognition, machine learning that we studied in prosthetics, same steps they used, and they got a trained model, right? And then when they send signals, then that gives you the output that is movement. Yeah? Okay? Understood? Yes? All right. So in both the examples, one is 1-dimensional, the other is 4-dimensional, but there is a similarity between both. What is that? You're taking signals and you're controlling something, right? You're taking signals from the brain and you're controlling something, either computer cursor, right? Choosing a letter or controlling an arm, right? Taking signals, controlling something. Okay. Is there anything missing in these BMIs? Is there anything missing in these BMIs? So you're taking signals and you're controlling. Ah.
Feedback. Feedback.
Feedback. Yeah. Thank you so much. That's it. Right answer. So is there feedback? Right? So you said it is missing, right? So is there feedback? So you're taking the brain signals and you're using those signals to control end effector, right? It could be anything. So is there feedback here? Was there any feedback? Yes or no? Yes. Somebody said yes, please raise your hand. If you say yes, please raise your hand. Okay, if you say no, please raise your hand. No, please raise your hand. Okay. And the rest everybody else are happy. Matlab, you had lunch. And wow, how does it matter? Yes or no? Kya matlab, exam paper already mil chuka hai. And answers already mil chuke hain. We already got answers. We already got exam papers. Why? Why this torture? Huh? So was there any type of feedback? Ah, thank you. So that's the right answer. Let's clap for him. Very good. Very good. So there was visual feedback. There was only one feedback. That was visual feedback, right? The person was looking, monkey was looking. What was monkey looking at? marshmallow, food, right? Right? Monkey was looking, the person was looking. So there was that visual feedback was always there. Okay. Right? The electrodes may not be in the visual lobe, right? Occipital lobe, but they are influencing in motor planning, motor preparation, etc. Visual feedback was there. Okay. That's a powerful feedback. We already talked about it, right? Visual, right? Visual learning. 90% of our learning is visual. Yeah. Okay. So that with that, we go to the trend 2 is from open loop to closed loop, right? It is only half the story when you take the signals from the brain and you're doing something. That is brain to action, right? Brain to doing something, that is brain to action. But how can I send sensation back to the brain? One way to do it is visual feedback. You look at it, your brain knows it, so that's easy, right? But if you're not looking at it, you remember the example where you're driving the car, suddenly cell phone slips out of your car. Remember that example? Are you looking? You're looking at the road. You're not, hopefully, right? You're not looking at the cell phone. So you're not looking. So then how do we give feedback? So remember when we cut the brain at the central sulcus, one side is motor homunculus, the other side is sensory homunculus, and they look alike, right? You see the two? They look very much alike, right? And they also have similar representations, right? This is motor homunculus, and this is sensory homunculus, and you can see that the tongue has representation, the face, the hand, the limbs, right? You see that? Yeah? So this is sensory homunculus, and this is motor homunculus. Now, how can we send sensation to the brain? This is the part of the brain that is taking care of sensation. Okay. Now you know that there is a physical part in the brain that is responsible for sensation. How do we send sensation to the brain? What can we do to send sensation to the brain? Huh? Electrical impulses? Where? To the where? Through electric. Okay. Yes. No, of course, not through current wires outside, right? Yes, we will use electrodes. Yeah. Through electrodes, we will put these electrodes where? We'll put these electrodes there. Sensory cortex, S1, right? Yeah. So if we put these electrodes, and right answer, let's clap for her. Yeah. So see, how are we reading intent? How are we reading what was decoded? We were reading electrical activities in the brain, right? Right. Now, how will you give input to the brain? You will also give it in the form of electrical activity, right? That's why you have to stimulate the brain. You send electrical activities to the brain, you are giving some type of sensation to the brain. Okay. So there's electrical stimulation. There's been a lot of primate studies that have been done in monkeys. Okay. Okay. Don't hurt yourself. Okay. All right. Okay. So but do you see any problems with that? Okay. So you're recording electrical signals, and at the same time, you're also stimulating, meaning you're sending electrical signals. Do you see a problem with that? Huh? Interference. Yes, that is one problem. What else? What else is a problem? There's a crosstalk, right? There's crosstalk, and you'll mostly end up recording the signals that you're sending. Then what's the use? Huh? So, okay, so if this is the problem, what is the solution? How can we fix this? Huh? You could use different frequencies. Still, they are all electrical signals. You're going to feel the shock. Huh? Create an inverse system. Huh? Filter it out. See, sir. Okay. Yeah, it's a good idea. It's not going to work because the electrical activities from the brain, they are very similar. The stimulation signals that you send to the brain are very similar to the recording signals that you're recording from the brain. So you can't have a model and you just, okay, delete. Doesn't happen, right? Yeah. but it's a good idea. It's again a good idea. So all good ideas. Yeah, let's clap for him. The first he answered the interference crosstalk, and second he said, why can't we have a model and delete these? Yeah. What else? What else can you do? How about we don't stimulate when we record? You got that idea? You should have shared, right? He got that idea, or you got that idea? Okay, okay. All right. So how about when we are recording, we're not injecting currents, we're not stimulating, right? Right? Will that work? Will that work? Yes. There would be time delay. And if there is time delay, what is the problem? And the same thing that you told, right, during the sense of agency, right? Yeah. If there is time delay, what is the problem? You won't feel it, right? When you are reaching and interacting, you are simultaneously moving and simultaneously you are feeling, right? You're sensing, right? It is all acting, it is all happening simultaneously. The action and the sensing, these are all happening simultaneously, right? Right? So, right, if you include a block time, so we will record, we will not stimulate. We will stimulate, we will not record. That will not be natural, right? That's a problem. So then what do we do? It's still all electrical signals. So then how are you saying? Uh-huh. Bless you. Mm-hmm. 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 What about the problems that Sir said? Interference, crosstalk, blurring. Can you avoid that? They are all very, very close to each other. Huh? However you code them, they're going to go into that, right? In our village, we used to have these cinema halls, small cinema halls, okay, with a TV. These are olden days, yeah, and there'll be two right next to each other. When the movies begin, you can watch two movies at a time. One you are hearing, one you are watching, because they're right next to each other. You can hear the movie that is running in the other room, right? So there will be crosstalk. There will be, however you decode it, however you encode it, there will be crosstalk, right? Then what else can we do? So this problem is all coming because we are recording electrical signals and we are stimulating using electrical signals, right? Can we do anything else? Who said that? Very good. How about exploring other options? Okay. Okay, you started it, but still, magnetism is what? Synonymous to electricity. Yeah. So if you stimulate magnetically, you're going to generate electrical signals. So get that idea. Okay. So what else can we use? One of the groups here had an idea. You had an idea. You had an idea. How do we record brain signals? Right? Remember when we did that exercise, sleeping batch? Yeah. You had an idea. You are the spokesperson, right? From your batch, you are the spokesperson. What did you say? How should we record brain signals? Huh? No, no, no. What? Really? Who said ultrasound? You guys were ultrasound, right? That's what I'm saying, yeah? So, okay, sit down. Let's clap. Let's clap. Sound. Instead of using electricity, we're going to use sound, right? Sound to stimulate. Yeah? Okay? That might lead to crosstalk as well, because anything you do to the brain, it could have electromechanical reactions, but at least it won't be as bad as electrical. Okay? If we have tried sound, if we have tried electricity magnetism, what else can we try? Huh? sound, electricity, magnetism. What else can we try? Huh? Very good. Light, right? You could use light, right? You could use light to activate neurons, and it is called, that area is called optogenetics. Okay. Towards the end of this lecture, I have another video. It's a TED talk to show how this works. But anyway, so you can close the loop. You can send sensation back to the brain. Okay. So here is one video. Okay. Again, we're going to watch this video and I'm going to ask some questions. Okay.
This is the region responsible for those electrodes have been connected by wires to a robotic hand with a tactile sensor fingers. Seeing as the trials take place, that as the response those physical sensations technical this range signals are the brain interprets by being blindfolded. Patients can identify with nearly 100% accuracy which fingers on the robotic hand are being touched. What does this mean for the future of neurotechnology? DARPA has previously shown that a brain interface can be used to direct the movements of a robotic hand. Now, with this new development of adding sensation by directly sending signals from the robotic hand back to the brain, we have closed the loop between them. At DARPA, we are always pushing the boundaries of what is possible. We view neurotechnology as one of the next great frontiers, enabling new ways for humans to interact with each other and with the world.
Okay. So, did anybody understand how that happened? Where were the electrodes placed in the brain? Where? Sensory cortex, S1, right? Sensory cortex. Okay. And how did the signals get there? What signals? What did the arm have? Tactile sensors, touch sensors, right? And what were they sensing? Pressure, right? So there was little pressure applied, right? So there was like little pressure applied, and that was being transduced into an electrical signal, and that electrical signal was filtered and sent to sensory cortex and stimulating the exact hand area, the fingers, right? You saw S1, right? Very clear representation. And the electrode was right there, and they were sending signals there. And when you put pressure, they can feel exact that, and they had 100% success. Yeah, make sense? Yes. All right. So this is trend 2. Okay. Wait. So what's the 3:45? Stop. Stop. Continue for some time. Maybe up to 4. Okay. Okay. Please check. Please check. Thank you. Okay. So while she's checking, we can continue. Yeah. Shall we continue for some time? Yes. Only one yes. Shall we continue? Is this interesting? Is this boring? Ah, yes. See? Okay, we caught 2. Madam, you said yes for boring. Huh? Okay. So trend 3. Trend 3 is taking these from lab studies into clinical trials. Okay. So there's a lot of primate studies that were done. Okay. There are a lot of electrodes that were implanted in non-human primates, monkeys, rats, mice, cats, large animals like pigs, and yeah, many other animals like that. These electrodes were implanted, signals were recorded, and robotic limbs like that were controlled. Okay. So after all those studies, after a lot of efficacy studies, FDA approved, FDA approved for brain implants. Okay, so let's watch this first video. This is from our study. We did this in 2013 in University of Pittsburgh. So 2012 was the brain gate trial. This video is very educational. So let's take a look at that. Okay. And again, watch the video carefully. We'll ask questions. Yeah. Okay.
Cells, which are actually in other parts of the brain, but they continue to function the same way after that original injury. It is possible for people to use their thoughts, control devices, either a computer or a robotic arm. The way that happens, we plant a tiny sensor about the size of a baby aspirin just into the surface of the brain. That sensor pick up the electrical impulses from a bunch of neurons. And each of those little neurons, like radio broadcast towers, putting it up impulses. When they get to the outside, they're translated, converts the pattern of impulses, something that is a from in. Yes, okay.
Yes, good stuff.
That when all of us saw it for the first time, it was all on. He reached out to the robotic, he thought about the use of real hands, he felt in terms of Rocky, brought it close to her, told it where it fell, and Rocky was strong. That was the first time in really 15 years that she picked up anything and been able to drink from it solely. There was a moment of true joy, true happiness. I mean, it was beyond the fact that it was an accomplishment. I think an important advance in the entire field of human interfaces, that it was really a moment where it helped somebody do something that they had wished to do for many years. It's the culmination of more than a decade of work, beginning with science at Brown University, that laid the foundation for all of the translational work that led from monkeys playing video games with thoughts to humans being able to control a cursor in 2006 to today's accomplishments. This kind of research can only happen when institutions come together and work together to see the scientists, engineers, and physicians work closely together to create the ultimate device, one that works 24 days, 7 days a week, works perfectly every time, and works real nice. That's what we're going to get. And we still have some distance to get them, but to know that it's possible takes all of us quite a career.
Good, interesting. Yeah. So this was when is it dated? 2012. Already 14 years. Yeah. So in this video, what did you learn? Where was the electrode placed? Huh? Where was the electrode placed? M1, motor cortex. Yeah. How many dimensional control did they demonstrate? Huh? How many dimensions did they control? 5. 5. 3 dimensions, right? Just the arm moving in the 3 dimensions. Even that was not full, they admitted. Okay. And so we also did similar. This is a small video, and after this we'll stop. Okay. So in this video, all right. In this video, we used, so in the previous video, they were using single unit recordings. In this video, we used ECOG, electrocorticography. This was done in our lab. Okay. I was part of this study. And so that individual that you're seeing is an individual with spinal cord injury. Okay. Spinal cord injury paralysis. Okay. And he was paralyzed for 7 years. Okay. So he could not move for 7 years. And this was the first time he was moving after 7 years. And one of the first things that he did was he reached out to his girlfriend and he did that high five. Okay. When he did that, he was crying. His girlfriend was crying. We were all crying. And there were TV channels when this happened. So they all recorded all that. There was science, there was drama, right? There's all that. And we became a huge hit. Huh? Everybody was watching us. It was everywhere in the news in India, in the US. Huh? So in the previous video that neuroscientist commented, right? This is what engineers can do. This is what engineers can do. This is what interdisciplinary engineers can do, right? Right? Everybody agrees? Yeah? Yeah? So this is what, so it's not mechanical engineering. It's not just biomedical engineering. It is not just electrical engineering, right? It is a culmination of many fields. That's why I kept saying the key word is interdisciplinary. You have to make yourself like that. Otherwise, you will be replaced by AI. AI can teach you better than me. Huh? So we will all be replaced by AI if we are not interdisciplinary. Okay? That's a big message. Yes? Yes? Okay? All right? Okay. So last sentence for today. Okay? You know how difficult is landing on the moon? Right? Even more difficult is putting an electrode in the brain. Okay? Now you saw all those nice maps of brain. When you do a surgery, when you look at the brain, will it look like that? It will never look like that. You still have to navigate yourself and land in the right place with your electrode. Then only you will get the right signals. Even if you make 1 micrometer mistake, instead of the hand region, you will be in the leg region. Some other signals you're getting. Okay? Make sense? All right? It is that challenging. Yeah? Isn't this field awesome? Brain machine interfaces. Yeah? But it requires interdisciplinary expertise. Yeah? Train yourself like that. Okay? All right. We'll stop here. Thank you so much. We'll do the test. We'll do the test now. She's checking. Are we doing the test? Or they're just checking? Break. We're going to take a break. Yes. Okay. After the break is the exam. Enjoy that, and we'll see you tomorrow. Final day. See ya. All right.